Okay, started recording again.
Oh, the one we did as a class was a really good one to do too.
Yeah, okay. I don't know what's going on with my word. Okay, anyways. Okay.
Start at the end or at the beginning? Go way up, because remember the hardest stuff was like at the end.
Let's just start at the end, I suppose.
That's probably the stuff that's still fresh in our minds.
So should we do some?
So hold on, what homework is this?
This is the impulse and homework.
I don't know. This seems very foreign. Like I've never seen this before. Okay,
Yeah,
I'll be back. Let me go get all my work. I'll be back.
Yeah, let me grab my book quick.
Oh my god. Rao is gonna make us do 50 questions in 50 minutes.
Wait, say that again?
Samita just said, she texted like in this one chat, she was like, Rao said she's making 50 questions in 50 minutes. Remember how Samita and Rao have this like friendship, so she just tells her everything, I guess.
Oh god.
Okay. But if they're like AP questions, then we have to read a question, like a long paragraph, look at a chart, and then answer a question. We're expected to do that in less
than. Okay, so let's see. Do you want to start with the other one, the class one? Because I know like not everyone did all of those problems.
Yeah.
Okay, let's start with that. Where's this?
Because I feel like we won't really learn, because I feel like we like on the ones we've already done recently, because I feel like we'll remember how to do those questions specific. You know what I mean?
Okay.
Aleena, there were pictures. Do you still have the impulse and momentum one open?
Yeah.
Can you go back for just 1 second?
Yeah.
I think I didn't print out one of the pages or something. Because something.
There's 5 pages.
There's 5 pages. Okay, that's the billiard ball one. Can you go down? Yeah. We have the billiard ball one. Okay. Conservation of momentum. Okay. Yep. Can you keep going down?
Wait, this is 8 pages.
I have that. Okay, that right there. I don't have number 20 and 21. Did she upload that newly or something?
I don't know. I remember one.
Oh, I don't know. Because mine doesn't have those for some reason. That's okay. I'll go back and do those later.
Maybe, yeah. Okay, I guess let's do this one. Let's do 20 and 21 then.
Okay.
For kicks. Okay, let me open 20. Okay, so 20, I don't know if anyone has a better explanation. Okay, so this is car 1. Oh no, my bad. Okay, so it says car 1 is traveling due north and car 2 is traveling due east. After the collision shown, car 1 travels due east. Which one of the numbered arrows is the only one that can represent the final direction of car 2? Okay, so car 1 is going north and then car 2 is going east. And so the way I did this was that this one I was a little bit confused about, but I like thought of this as like vectors. And so it was like car 1 is like this, and then car 2 is like this. And so then the vector would be like this. So then it would be number 4, which I believe is the right answer.
Yeah, it's the right answer. I think she wants us to maybe say like conservation of momentum, you know, like how it has to be the resultant. So if one's going like this, then the other one must be the resultant of those two.
Yep.
Yeah.
That's exactly it. So you said that car 2 must be going. Which one did you say was the answer?
4.
You said 4 was the answer. Yes. Okay. Yep. Okay.
Okay, and then number 21. A fan and a sail are mounted vertically on a cart that is initially at rest on a horizontal table as shown in the diagram. When the fan is turned on, an airstream is blown towards the right and is incident on the sail. The car is free to move with negligible resistance forces. After the fan has been turned on, the car will Okay, so we look at this, and so it says the fan is turned on, the air is like pushing the sail, right? And then they're mounted that is initially at rest. Okay. Okay. So it's initially at rest, and then it's blowing towards the right. And so I remember the answer, but I don't remember why.
Why? Yeah, I remember it says that it remains at rest, right?
Yeah, but I don't remember why exactly.
I don't remember MGG.
The cart remains at rest?
Yeah, that's the answer.
That was the answer.
That I'm not sure why. Let's see. So if we use law of conservation of momentum, M1, it's starting at rest, right?
Yeah.
So I guess you could say the system has a velocity of 0, or this whole system has a momentum of 0 in the very beginning.
Yeah.
And then at the end, you have, I guess, velocity blowing. You have the velocity kind of the air pushing this way on the sail. So I guess M1 V1, and then that's the velocity of the air, and then I guess you would have minus M cart V cart. So shouldn't the car move, or shouldn't the cart move to the left then?
I don't know. I think that's what I initially thought, but that was not the answer.
And also, if the
That's
air
what
is
I put as the
on the
answer, but I
sail
said that-
this way, then why wouldn't the car move forward?
Let's search.
It's a very weird question.
I know.
Yeah.
That's what I tried to use conservation momentum, and it didn't prove why it remained at rest.
Yeah.
There's no, wait, are there
Take
no
off the
answers for
answer.
these?
I remember there was an answer, but I guess it's not there anymore.
I know. I remember the exact same thing. I remember those two
Yeah.
questions. I remember the answers that they had, but I don't know where I saw them.
Yeah, me neither.
I know for sure the answer was B though, and because I remember I was really stumped by it.
So yeah, I'm not sure about this one. Maybe the answer key was wrong.
I think
Can you search that one up online?
Huh?
Can you search that one up online?
Yes. Okay. Assignment expert.com. Okay. Okay, so okay. As well as the fan applying a force to the air molecules apply a force in the opposite direction, equal in size on the fan. So we have two forces acting on the cart, one on the sail and one on the fan, which are the same size but in opposite directions.
I thought they said no resistive forces though. If there's no resistance forces, then why are the air molecules pushing back on the fan? I mean, pushing.
Yeah.
As well as the fan applying a force to the air molecules apply a force in the opposite direction, equal in size on the fan. So we have two forces acting on the cart, one on the sail and one on the fan. This doesn't quite make sense to me.
Isn't it also like kind of arbitrary though? Because isn't it like there's a certain amount that the sail can hold before it starts to move, and like how much, you know what I'm saying? I don't think that any amount of wind that could be true.
What? This does not make any sense.
We're saying both forces cancel out.
Yeah.
Yeah, this doesn't make sense to me.
Okay, let's go back. Okay, let's look at one more and then see if we can find it. Studentroom.uk. Wow. Okay. Okay. IBH. Oh,
I would never trust intuition. So there is an equal and opposite reaction on the fan putting force on the air, which reaches the sail will result in the air putting an equal force on the sail.
But
Okay,
I don't. I
so
get
fan,
that, but why? I get that, but why does? But how? But doesn't that not matter if it says like negligible resistance forces?
That's what I was thinking too. So fan puts force on air, and thus
Yeah.
air puts force on sail, but then the sail puts a force on the air, and then the air puts a force back on the fan. So
Yeah, that's so weird.
I see. So it's not, it doesn't have to do with resistance forces, I think. What's happening is, here, can I annotate on here? I think,
Yeah. Also, please tell me if you can hear my parents talking.
We can, but it's okay. It's not like overpowering or anything. It's fine. I can't. We can't tell what they're saying. We just know that
Okay.
something's happening. It's
I'll just
okay.
mute myself when you're talking.
Okay. So we have the fan. Let's pretend that this is the air. I'm going to pretend that the air is an object because it's easier to think of it that way, I think. And then we have the sail. So the fan is pushing on the air, and the air is pushing on the sail. But so we would expect it to go forward, right? But because of Newton's third law, or okay, basically what's happening is this transfers its momentum to here, and this transfers its momentum to here. But because of Newton's third law, this force, because the air pushes on the sail pushes back on the air, and then the air pushes back, it transfers this momentum onto the fan, which is why it doesn't move.
Oh, okay. That's really weird.
It is weird.
I didn't like that question. Okay.
I mean, if we had this in real life, right? If we had a fan going and we had a sail, I would expect it to move forward. Oh, but okay, yeah. Because okay, that's right. If you had the fan on its own, then it would move. The sail is what's stopping it from moving. If the sail wasn't there, then it would move. Can you imagine that, right? If the fan is moving, it's pushing the air, but there's nothing to push. But yeah, so then it would be moving. Okay. Got it.
Okay. So should we do any others on this one, or should we move or to like the one we did in class? Anyone have any?
I think if
sorry, I had one question actually. I never understood this one. But could someone explain number 18? I still don't understand it.
okay. What's if I saltary, throw, bounce, catch? So perfectly elastic means that no energy is lost and all the energy is transferred to the other object.
Oh, this one's very simple. I don't think this has to do with energy. This one, if you have your astronaut here and you have the ball, which is the same mass as the astronaut, and you have the wall here, right? When the astronaut pushes this ball away, he too goes away in the opposite direction with the same speed, because their masses are the same, right? So to conserve momentum, they start going apart. By the time the ball hits the wall and starts bouncing back, there's now a constant distance between them, and the ball never reaches so what happens is, think of this as initial hit contact, or initial point, and then I guess the ball will hit the wall, and by that time, let's call this a distance d, then the astronaut would have also traveled a distance d, and by the time, then if we call this point 3 or time 3, by the time the ball comes back here and comes back to distance d, or if we call this x equals 0, comes back, travels back a distance d, the astronaut would be at 2d, and they keep moving it with the same velocity. So that's why it would never reach the. Yeah.
Okay, that makes sense.
Okay, how do I clear? There we go.
Okay,
Wait, wasn't there a number 22? Did we do number 22?
number
Or I mean
22.
at the very end.
Yes.
Two
Okay, so
spheres
this
collide, which
one,
is the following. Okay.
the two spheres are moving towards each other along a straight line. The spheres collide. Which of the following gives the total change in linear momentum of the spheres as a result of the collision? Okay, so wait, what does it say?
It's just C, right? Are they?
This one?
That would just be C, I think, right?
Yeah. Why did I on A?
Oh, if they were the same mass and the same velocity, then I guess. Wait. Yeah, if they were the same mass and the same speed, then they would be 0, I think, right?
Massive, same straight line.
Oh, wait, it is A because it's asking for change in linear momentum.
Okay.
Change in momentum is always 0 because of conservation of momentum. The final momentum itself would be D. Yeah.
Yeah. Okay, yeah, because the change in momentum is 0 because this is a collision, and so there are no external forces.
Yes.
And
I was wrong. Even if it was afterwards, the answer wouldn't have been C. The answer would have been D.
Yeah, the final. I mean, like the. Yeah. Okay.
Okay. All right.
All right. Let me just double check that. No questions here. Okay. Yeah, I think that is it. Okay. We can go to this one. That's right. Okay, so has anyone like done all of them or like has any question on any of them? If not, we can just do one.
Are there any more spring force questions? Because I'm not great at those.
Okay,
like the Hooke's law questions.
We can do these, but also just FYI, Miss Raja asked me to do them, and I did them, and she posted my solutions on Schoology. So if you wanted to look at them later as well, but we can definitely do them right.
Oh yeah, they're here, aren't they?
Yeah.
Okay. Okay, so I think these are some spring questions.
Okay. 17 I understood, but 16?
16, okay.
It's just I haven't seen this question, but
an ideal spring with a pointer attached to its end hangs next to a scale. With a 100 Newton weight attached, the pointer includes 40 and indicates 40 on the scale as shown. Using a 200 Newton weight instead results in 60 on the scale. Using an unknown weight x instead results in 30 on the scale. The weight of x is... okay, I'm not very good at these spring questions either. So, okay, let's see.
I have just a real quick question before we start this. So whenever a spring is coiled above equilibrium, like it's what's it called, condensed, then it has elastic potential energy, right? Because but once it stretches below equilibrium, then it has lost potential, or it's lost energy potential, which as lost potential energy. Or kinetic energy, sorry.
Hold on, let me check just to be sure.
Sorry, say that one more time, Maham.
I was saying whenever a spring is condensed above like equilibrium, what is equal, like is that just like its normal state? Is
equilibrium is where the spring would be if there were no mass.
Oh, okay, yeah, that's what I'm talking about. Yeah. So if it's like condensed, like the spring is condensed, then that means that it has elastic potential energy, right?
Yes, it has elastic potential energy.
And then once it drops like below, like when there's a weight, like a mass pulling on it.
So when
If
it's
there's a
stretched.
mass pulling on it, there's also elastic potential energy.
Okay. So what is like, is that like negative or I'm the kind
So
of
whenever you have potential energy and kinetic energy, it depends on what you start off with. It depends on your final and initial position. And it's hard to explain without doing a problem. So number 16 probably isn't the best problem to show what we mean. Number 18 is a good problem to do that, and then number 15 is also a good problem to do that. Number 18 is probably the easier one though.
Yeah.
Okay, yeah, we can do number 18 then. I don't know, does someone else want to do it just for fun? Maham, do you want to try doing it, I guess?
I can try, but I don't really know what's going on. Okay, I'll try. An ideal spring is hung vertically from the ceiling. When a 2 kilogram mass hangs at rest from the spring, it's extended 6 centimeters. So 2 kilograms, and then it extends 6 centimeters below relaxed length. The downward external force now applied to the mass to extend the spring is an additional 10 centimeters. How much work is done by? Oh, haven't we done this question? This is the really strange one, right?
Yeah, you're in my class, right, Maham?
Yeah.
In physics. Okay. Yeah, we worked through this one.
Yeah, we did this one already. I think.
Oops.
Do you understand how it works, though?
Can you explain just a little bit more one more time, because I was like really lost during class.
Basically, you can calculate using, because work is change in kinetic energy. So the work being done by the object, because we can only calculate, actually, what can we calculate? We can calculate the change in potential energy, but elastic potential energy. But what we'd be doing is we'd be calculating the work done by the external force. To find the work done by the spring, the work done by the spring is minus work done by external force.
Nothing. Yeah, continue.
So if you can calculate delta EPE, then you can calculate work done by the spring.
Okay.
Okay, does that make sense?
I think so. Yeah.
Okay,
we can work through it. I mean, but I think that, I mean, can you go down to the solutions? That way we don't have to like draw it out and everything again.
Okay.
So the first thing you want to do is calculate the spring constant, because otherwise you can't do anything with it. So just using k equals f over x, you can figure out, and the only force acting while the mass is on there is mg. The displacement by that will give you k. Now you know that the work done by the external force is change in elastic potential energy. The reason for that is the spring force is a restorative force. The spring force doesn't act on the mass. It's not acting downwards. It's acting on the spring, and it's pulling the spring back to its equilibrium position. And whether it's above, if it was compressed, say the spring was compressed, then it would be pulling the spring back to its equilibrium position. So that's why its work spring is negative delta EPE actually.
Okay. So elastic potential energy is calculating the you have to, that's the external force. So the negative of that would be the force done by the spring.
Yes, the work done by the external force is causing a change in elastic potential energy. That's how I like to think of it.
Okay. Should we do another one, maybe?
Sure.
Okay, so you said number 15. Is it number 15, right?
Sure.
Okay. An ideal spring is hung vertically from the ceiling. When a 2 kilogram mass hangs at rest from the spring, it is extended 6 centimeters from its equilibrium length. An upward external force is then applied to the mass to compress the string, so it is 10 centimeters shorter than its equilibrium length. While the spring's being compressed, the work done by the spring is blank. Okay, so should I do this or?
Sure, go ahead.
Okay. Or do you want me to work it, or do you want to just look at the solution? I don't know.
Do you think it'll help you if you work it?
I think I did this one, so I think I kind of remember how to. I think this was one of our group's like questions.
Okay.
Okay, so let's look at the answers. Okay. So here we can see MG drew this. Okay, wow. There's a lot going on here. Okay, so number 15, we see, okay, so it says a mass of 2 kilograms is extended like 6 centimeters. And then it says that it's extended like 10 centimeters shorter. And so you put 0.1 meters. And so like MG put here, the work of the spring force is equal to the work of the external force. And so the work of the external is equal to the change in elastic potential energy. And so that's equal to, okay, I think because it's, okay, yes. So it's going to be negative delta EPE. So we have negative 1/2 K delta X squared is because we're having a change in like the length because from 6 and then 10 meters shorter. So then we have, oh wait, I should have said this first. Okay, so first we're calculating the, first we're calculating the constant. So we do K equals F over X. So same thing we did in that other one. We do mg over x because that's the only force acting on it. M is 2, G is 9.81 or 10 or whatever you're using. And then X is 0.06 because we're first trying to figure out because we're using the first sort of extension. And then we get 327 newtons per meter. And then we plug that into negative 1/2 K delta X squared. And so then we put K as 327 or whatever you got if you use 10. And then we do 0.1 minus 0.06. I mean, like you square each of them. And then when you subtract them, multiply that by 1/2 of 327 and you get negative 1 joules.
The other thing is sometimes you'll see in textbooks, they'll write the spring force is actually equal to negative kx to show that it is a restorative force. So depending on what you designate as your coordinate position, like I'd rather just look at the magnitude F equals kx and then figure out the signs later, but sometimes they'll put the negative. So then K would be a negative number and you wouldn't need to write W spring, work done by the spring equals negative change in EPE. Sometimes people just say work done by spring equals change in EPE, given that your K is negative.
Okay. So for this one, you have to do like x2 minus x2 squared minus x1 squared because it said that it's like 10 centimeters shorter.
You always have to do x2 squared minus x1 squared. Always.
Okay.
It's just that sometimes x2 and x1 are in the same direction, so it doesn't matter. And x2 and x1 are always from the equilibrium position, always. Okay. Whereas when you're doing potential energy, gravitational potential energy, all that matters is the height and the initial, and you can figure out where 0 is. It doesn't matter. But in springs, there's always an equilibrium position, and that equilibrium position is always 0.
So if x and x1 are in the same direction, you would, instead of subtracting, you would add them together?
Well, you're still essentially doing the same thing. You would still be doing, for example, if it was number 18 where it's in the same direction, you would have 0.16 squared minus 0.06 squared. But that's essential. No. Actually, you'd still have to do x2 squared minus x1 squared always, because it's from the equilibrium position.
So even if they're in the same direction?
Yeah, even if they're in the same direction.
But
write that down so I don't forget.
Because the formula is negative 1/2 K delta of x squared. Right? because EPE is 1/2 kx squared. So if you take delta EPE, it's negative 1/2 kx squared final minus negative 1/2 kx squared initial. So the x squared, it's not delta x quantity squared, it's delta of x squared.
Okay. And so then, can you just say again, why is it negative EP, like delta EPA, EPE?
Because if you go back to the PowerPoint, it'll, I think it explains it well in the PowerPoint, is that the change in elastic potential energy is the change in elastic potential energy is the work being done on the system. Yes, the change in elastic potential energy is the work being done on the system. So the work being done by the system is negative of that. Think about it in terms of gravity, right? If I lift my mouse from here to here, the work that's happening from here to here is the work being done on the system. But the work being done by the system, by gravity, the work being done by gravity is negative because I'm lifting it up. It's the same thing with springs. Whatever work you're calculating is work done on the system because you're up. That work is being done to create some sort of energy, some sort of change in energy. You're doing it on that system. Yeah.
Oh, okay.
So when you're finding K and you're doing like your force over X, if you were to write like the mass times negative 9.8, then you would get then you would get negative EP.
Okay, I don't take G equals negative 9.8 because, yeah, rather than, I always deal with the signs later because if you start dealing with the signs in the middle, like positive and negative, it gets very convoluted. Things get very, very convoluted if you try and put signs in the middle of the process. It makes more sense to calculate the magnitude of things and then figure out whether it's positive or negative based on, distance and your coordinate system.
Okay, that makes sense. I think like because we just learned springs, I think that's definitely the most like confusing thing to me. So okay.
Well, you have like 1 minute 40 seconds just left, just FYI.
Yeah, I noticed. I don't know if anyone has any other questions. I don't know. Should I restart it? I mean, we've been here for like 30, almost 40 minutes.
I don't really have any questions right now, honestly.
Does anyone else have any questions? I don't know. If not, then we can just end it when the meeting ends.
I think Anna had a question about orders of magnitude. So
oh, she said,
just
wasn't there that rule that it was like to the power of 5, something like that?
Well, I mean, what I do is I just take the nearest. So I take the nearest power of 10 for the first object, the nearest power of 10 for the second object, and then I divide them. That's how I do it.
Yeah, I know. I thought there was some like rule that she said.
Oh, I don't know. I'm not sure.
Remember. Yeah, none of us remembered, so that's why.
Okay.
I couldn't find it in my notes either.
Otherwise, I think I'm good.
Okay, I'm going to stop the recording then.